I like it.
Math.
Math.
Fake math.
You hate math?
Fake math.
Oh, fake math?
That's what calculus is. It's just fake.
Interesting.
I feel like a lot of math past
That's
like
a-
algebra
that's
is
a
just
hot
fake.
Algebra is fake.
The math that every other math is built on is fake. That's crumbling my whole foundation. Sorry. Anything? So does anyone know? Somebody said something earlier before the class started. So a few of you guys probably know one of the more famous. Believe it or not, there are like famous sequences. Let me just say this person's name. Starts with an F.
Fibonacci.
There's all kinds of jokes. Like you can make Fibonaccios. You can eat them 1, 1, 2, 3, 5. Okay. So this sequence goes like this. Now, if you know, don't say anything. If you've never seen this before, can you tell how that sequence builds? Do they just look random, or do you see anything tying those numbers together?
Add the two numbers.
Yeah, 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. Right? Okay, I like it. So let's talk about a couple of notation parts that we're going to use. Some notation we're going to use. A sequence is denoted by AN. So you can talk about the sequence AN, you can talk about the sequence B sub n, right? I'm going to call them AN, BN, CN, and so forth. So like, for example, and sometimes we'll even put them in little brackets. So for example, this one would be A1 is 1. That's amazing. A2 is 1. A3 is 2. So the little numbers tells you which element of the sequence you're referencing. So that makes, hopefully, immediate sense. Look at math people doing something that makes sense. Now, the way you write the rule for a sequence is depends on what the sequence pattern is. This one is a stranger pattern. Its elements are based on the elements that came before, right? That's how this sequence is built. So it's what's known as a recursive sequence, something that's built on itself. So I wanted to start with this one because I knew a few of you guys have heard of this one before. This is one of the freakier types of sequences. So we're going to kind of take a step back in a minute and look at the more basic ones. But I thought this is a decent way to introduce some notation. And one of the weirder things, recursive sequences. When you see the word recursive, that means it kind of is self-generating, right? It kind of creates itself. Give it a rule and it creates itself. But tell me this, what are the two most important numbers in that sequence? 1, 1. You got everything started, right? So with recursive sequences, you have things called seeds. So in this case, how many seeds did I have?
2.
2, because the general rule is 2 sequence elements add to make the next one. How are we doing so far? Can't like it. By the way, if you've never heard of Fibonacci sequence, please go home, and when you get home, just Google Fibonacci and then anything you're interested in. You guys have any interests? No. Any interests at all?
Go Fibonacci
Okay, that's good.
Minecraft.
I just do homework.
So just type in Fibonacci nihilism. I don't know. So type in Fibonacci music, Fibonacci surfboards, Fibonacci.
Is that it?
Huh?
Is that a thing? Surfboard?
Yes. Somebody made a surfboard that kind of is modeled on the idea of this Fibonacci sequence. Okay, anyway, a friend of mine, real quick, who was making stupid amounts of money so he could play in the stock market a lot. He made money through the recession, which is what happened when you guys were little kids.
2008. 2008.
Yeah, 2008. He made money using the Fibonacci sequence. It would be the certain number of dips, and then he would know when to put money. He made money using a Fibonacci kind of idea applied to the stock market.
That's scary.
Which is insane. And I am not selling it to you. I'm not doing any of that shit. I don't care.
Yeah.
It's just I haven't even looked at it because I don't have money to play in the stock market. So hey, why would I care? But anyway, there are many, many, many recursive sequences. This just happens to be one of them. Can we come up with a rule for this using this notation? Oh shit.
Apparently.
How do we get A3? Go ahead, sorry.
AN minus 1
Ooh.
plus AN.
Ooh. Equals?
AN plus 1.
Yeah. Let's see what the hell this says. To get the n plus 1th term, I take the n minus 1th term and the nth term. What the shit? So, if I want the 3rd term, what would n be? 2, yes? So if n is 2, what is this? A1,
Plus A2.
A2 equals A3. Is that true?
Yes.
Yes. And that would be true anywhere you are in the sequence.
Does that work with n equals 1?
Oh, obviously, you gotta, the seeds are normally considered, what do I want to say? Yeah, if n equals 1, something weird happens here, right? Yeah. So once you get past the seeds, then the rule starts in. So A0, or I'm trying to remember this book, if it starts at 1 or 0, I think it has both. This one and this one are kind of given, and then the rule kicks in. So without the 2 seeds, the rule wouldn't make any sense. I like it. So you can't start at 1. You have to start at 2. Good catch. All right, are we doing decently well? That's one of the weirder ideas, by the way, is the idea of recursive sequence. Okay. So yes.
So just to like make sure I get it, so 1, and the first 2 ones would be the seeds, and that's what kickstarts the entire sequence.
Kick ass. All right, let me show you a couple other things about this, and then I'll do another example with different seeds. Something about Fibonacci sequence. Can you guys just help me go out a few more places? 34.
55. 89. Crap.
144. All right, that's good. What is 34 divided by 21? Help me out.
1.6190477.
All right, that's good. What is, let's go a few more in. 89 divided by, it's like, yeah, just stop me. What's 89 divided by 55? So one term divided by the one previous.
1.618 repeated.
Okay. And what's 233 divided by 144?
1.61805.
And it will be that forever, right? So that's interesting. There's so much to this. Everything I'm about to say is nothing you have to know. So I just want, whenever I say that, I want to see somebody go, all right. This is kind of cool. Have you guys heard of what's called a golden rectangle?
Golden ratio.
Yeah, the golden ratio.
Yeah.
Right. So this is what's known as the golden ratio. It's given the symbol. It's a phi or phi, depending on how you feel. Right. Phi, phi, fo, fo. No, it's just phi or phi. Greek letter. Right. Stay with me for a minute. I'm not going to go too deep into this because I mean you could have an entire, you could have an entire lifetime studying this shit. Holy shit. So we're not going to do that. We're just going to take a minute. A golden rectangle. Oh shit, now I have to come in here incredible. Is one such that where you cut this and you make a similar rectangle to what the rectangle was to begin with. And of course, I didn't write this down, so I can't remember right off the top of my head, but the ratios of the sides come out to be 1.618. Now something that I didn't even get this right, I just thought I did. Then you start to think, I went to a conference a while back, a math conference, of course, right? Where we just sit around and say math, 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 math. And somebody was doing this thing about different shapes, different polygons with similar ideas of, so there's like a golden pentagon and a golden whatever. And I said to them afterwards, I'm like, did anybody look at the sequences that would be related to that? She said no. So what did I do? I found the sequences. And went, so it's like one thing I've done, and I haven't really put it together to be like a thing. So anyway, sorry. That's just to give you an idea. When I have free time, what do I do?
Math.
Yeah.
Yeah.
Yes.
Does that work three-dimensionally too, or is it
Dude,
one-dimensional?
that's the next. That's something that they're working on, and I'm like, I'm not ready for that. Yes.
I believe it's a square, so you
No, it's
carve
a
out a
rectangle.
perfect square, and then the golden rectangle is left over. And
Yeah,
then
it's
keep doing that.
I think you're right. I can't remember. It's A, B. This might be A.
Yeah.
A to A plus B. I'd have to look it up to be right.
And
But
then
it's sort of like, let me see if I can remember.
And then it like
A
spirals
to
out.
A plus B is equal to B to A, I think.
Mm.
Sounds about right. Anyway, I'm not going to do too much with that. Yeah. Thank you. But if you ever do any art, there's not really a hard, fast rule, but you're not supposed to really center things, correct? And this is about when they show people a rectangle with like a different color here or something placed here, it is chosen as the most aesthetically pleasing the closer that I get that dividing line here. This is the connection between math and psychology, math and aesthetics, math and music, math and everything. So it's unfortunate we don't have more time. We don't have any more time. That's all I time we got. So, yes?
Is that idea where the spiral?
Yeah, it's an unfortunate thing. The spiral is actually a logarithmic spiral. It's not really a Fibonacci spiral, but it's close. It's really close. But you'll have the nautilus shell, right?
Yeah.
And the spiral is actually a logarithmic spiral. It's not. It's an Archimedean spiral. It's not a Fibonacci spiral, but it's really close.
Okay.
So that spiral idea, I can keep doing this, by the way, right? I really want you to understand. So I take this rectangle and I slice it somewhere so that this rectangle shrunk. And then I can do it again. This rectangle shrunk. And then I can do it. Okay. And if you connect all the edges, you'll get this neat spiral that happens, which if you lay it on top of a chambered nautilus shell, it looks like it lines up. Doesn't quite, right? But it's pretty close. Anyway, okay. The number of tree limbs, if you look at a tree that hasn't been through injuries and stuff, it'll have, as you go up, it'll have one, and then I'll have two, and then I'll have three, and then I'll have five, and then I'll have, so it's the way that nature builds on itself is kind of captured in this sequence, which again is really kick-ass if you have more time to talk about it. That's more time than I had to talk about it, so that's it. All right, so that's one thing, and it kind of introduces the idea of recursive sequences. Real quick, just to give you an idea of other things that math people do when we're Fibonacci. This is an actual person. This is something you might be able to guess. Instead of 2 seeds, it has 3, right? And so you add 3 to get the next one. 1 plus 1 plus 3 is 5. 1 plus 3 plus 5 is 9. 3 plus 5 plus 9 is 17, blah, blah, blah. And you'll also get a limiting ratio. I think it's 1.7 something, can't remember. 1.75 or something. Anyway. All right. How you guys doing so far? Yes?
Does that, so obviously it would change the size of the rectangle, but would it make it exponentially?
This could be related to something 3-dimensional, right?
Okay.
Yeah, because now you got these 3 components, so it might be length, width, and height. Yeah. Okay, I like it. All right. Okay, so now watch this. One more thing about recursive. Let me give it to you like this. One more recursive, and then we'll take a step back and do some more simple stuff. Recursive sequences. What if I said, let me make sure, I always forget if this book, yeah, it kind of does both. Okay. Some books start at 1, some books start at 0. Let's say A1 is 5, A2 is -2, and N is AN minus 1 minus 3 AN minus 2. So I've given you a rule to flesh out more elements of the sequence. Now this should be the one you guys can really sink your teeth into, because all you gotta do is plug shit in. So these again are called the what? Seeds. These are the seeds. Look at that. It's stereo. So I can't plug a 1 or a 2 in, because mathematically it wouldn't make sense, but I also don't need it, because they're just given to me. So what's the smallest value of n then that I can really use? 3. So if n is 3, take a minute and see if you guys can figure out what that is. So it really is just plugging the value of n in. Hold on. So if you just plug 3 in, what's this? A2 minus 3A1. A2 was -2 minus 3 times A1 was 5. So yeah, you get -17. You know, so I can give you this kind of problem, and I can say, find the first 5 terms of the sequence. Do you like that kind of problem?
It's easy.
Does it almost not matter what the hell I'm learning? This is a kick-ass problem. Just shove shit in. It's like, please, Jeff, give me that. Just plug stuff in for n. Yes? Please love that. Okay? I like it. Yes?
So if you ask us to find like A7, you have to find.
Yeah, the really sucky thing about recursive formulas is it's not easy, it's not impossible. In fact, that's part of what we're gonna do. But what if I want to know the 80th? Let's just go crazy. What if I want to know the 80th sequence element?
Gotta do them all.
What's the only way I know how to do that?
By computing.
Good. Shit. Right? And the whole idea of mathematics is finding a pattern so it can find a shortcut to get somewhere. Right? So let's take a step back then. Take a step back to the more basic sequences. So I sort of started in the middle. I started with the middle idea of recursive sequences. Okay. So of course, one thing I wanted to point out there is I could have a rule, and then I could go back and change the seeds and see what happens to the sequence. Correct. Okay. So what about, let's take a step back. Just basic sequences. So if I define a sequence like this, what do you got, John? Sure, 11. Is this recursive? No. Why is it not recursive?
Because it doesn't build
rely
back.
on past terms.
Yeah, the equation is not dependent on earlier sequence elements, right? I can now get the 80th element easy, right?
Yeah.
So a basic sequence defined like this is not recursive. I can get whatever sequence element I want. It's not built on itself, so I can just go straight there.
6320.
What would the 80th sequence element be?
6,320.
I like the 80 squared minus 80, 6,400 minus 80, 6,320.
Yep.
I like it. So if I ask you to tell me the first 5 elements of the sequence, you should all go, yeah. Yes, thank you. Don't ask me to integrate cotangent anymore. Yeah, I am still going to do that, but not for a little while. So what's the first 5 elements? What's A1? 0. What's A2? 2. All right, I've already poured. Okay, so that's easy. Yes. Please let that be easy. If it's not easy, go ahead and ask. It's okay. But this really is just a function. It's almost like a function notation. Except, does anyone know why we use the letter N?
No.
It's
Like
n,
population.
integer number.
Natural numbers. Right? And what are the natural numbers? The things that came naturally to us.
Positive.
1, 2, 3.
Right? And I don't know why our number system is based on 10. Who knows? We'll never know. But
Based on
like 0 had to be invented. There were whole civilizations that had no symbol, and some of them had no real concept of 0. right? So we had to invent 0. So we're all standing on the shoulders of a lot of shit that was done. Okay. So that's why I put it in here. That's why normally I like it when it starts with 1, but sometimes they start at 0, which sort of goes against what n's supposed to mean, but oh well, we're cool. Okay. All right, maybe. Okay. Let me see. I've got an outline of what I want to talk about. Oh yeah, let's do this. So that's one where I gave you the sequence generator. So sometimes it's called a generator. You can see why, because this sets up how to generate sequence elements. So what if I give it to you the other way? What the hell does that mean? What if I give you a sequence that's already made and you have to come up with an? So for example, so you need to figure out, no, don't say anything yet. If you figure it out, don't say it. You need to come up with the an that would have generated these elements. So this is A1, so forth, right? Can you see obvious patterns? So one thing to notice about what could really suck about fractions, if you get a problem like this, in this case it didn't work that way. None of these are reducible, correct? But we'll look at another one that the book gave as an example, that if you reduce them, it makes it much harder to think backwards. So we'll talk about that. But looking at the numerators, what are they?
They're all
Multiples of
2.
the numerator. What did I said? Numerator.
No, multiples of 3.
All right. Sorry. I was like, what did I say? All right. Yeah. So A1 is 3 over 4. A2 is 9 over 8. So this is 3 to the first. We're going to worry about the bottom in a minute. This is 3 squared. So you see how that lines up beautifully, correct? And do you see exactly what I'm doing? Write A1 equals that. A2 equals that, and then start looking to see. Now, what's the whole idea? AN equals stuff with N. I need to figure out, for the first one, how does the number 1 factor into it? For the second one, how does the number 2 factor into it, correct? Because the equation that generates it is a function of N. So that's why I do this, A1, A2. All right, 3 to the first, 3 squared, 3, oh, cool. So what's the AN for the top? 3 to the end. And of course, the bottom is a little bit trickier. What are they all based on? 2, but this one's 2 squared. This is 2 cubed.
So 2n plus 1.
This will be
2
to the 4th. Yeah, I heard it.
2n plus 1.
2 to the n plus 1. It's just one more than the n you're at, right? If you're at the first one, this is 2, so it must be an n plus 1 up there. Now that can very quickly not only get difficult, but nearly impossible to be given a list of numbers and to be able to tease out. Now I made a nice easy one, but they are definitely not always easy. Okay, let's do a couple of easy ones, and then we'll look at a freakier one. Everybody understand this idea? So if I give you a generator, easy as shit, just plug stuff in for n. 1, 2, 3, 4. If I give you a sequence and ask you to come up with an, that's a little harder, of course. That's backwards, right? So you're going to have to actually do some work and figure out, well, what's the connection? Okay, maybe. You guys with me? Okay. So let's do 2 easy ones, and I'll tell you what their names are after we do them. So what about if I give you this here? What do you got, Jeff? All right, this is a nice one. Let's see if you guys. Let's see if I can add correctly. Okay. Yes, Jeff. Yes. But this is going to be interesting about how to capture the generator, how to capture the n, the function of n. So what is the obvious pattern here?
Add 3.
It keeps doing what? Adding 3. Blah, 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 blah. all the way through. Everything I've given you so far. So the minute that the dot, dot, dot there, that means the pattern holds. Now the funny thing is, real quick, I could generate a sequence and have in mind a pattern, and then you see a different pattern. Are you with me?
Mm-hmm.
Because if I just said 2, 5, can you tell me exactly what I have in mind? No, because maybe my mind is n squared plus 1. Right? 1 squared plus 1 is 2. 2 squared plus 1 is 5. Nah. See, I would be not evil because I would accept it. I would say, oh shit, I didn't even think about that. Oh, it works. Okay, sweet. I would take it. But normally I give you enough, so there's only one possibility. You guys know something? If you Google 1, 1, 2, 3, 5, and actually there's a sequence database. It'll actually tell you which sequence that is in the database. And it'll tell you properties of the sequence. I know. Ultra boring sounding, but it's actually kind of cool, right? Okay. Does anyone, you guys know how to write this
3n minus
function?
3n
One?
minus 1.
3n minus 1?
Yeah.
Okay, let's check it out. If n is 1, this is 3 minus 1. If n is 2, this is 6 minus 1, right? 5. That looks good. So you notice that the slope is 3, correct?
Mm-hmm.
Does that make sense? Right?
Oh.
As the element goes from 1 to 2 to 3, each output increases by 3. That's slope.
Uh-oh.
So arithmetic, this is called an arithmetic. What do you mean, uh-oh? You came up with the idea? This is called an arithmetic sequence. It's kind of nice, A for add. Not really, but you know, it's a way to remember.
Is there a way to derive the 3n minus 1?
Yes, let's do it this way. Let's do it this way, you ready? Now watch. So A1 is 2. A2 is 2 plus 3, yes? A3 is 2 plus 2 3s, yes? Let me write this. So this is this, and this would be this, right? So one way to think of this is start at 2, and then I take no steps from, and I start at 2. I take 1 step of 3, so now I'm 5. 2 steps of 3 away from 2, right? Are you with me? And the minute you can write it like this, you can capture a connection between what element you're at and how you got there. What is this formula now?
2 plus 3n.
Plus 3 times n minus 1. Good. You with me? Good, right? Because that's 0 when that's 1. That's 1 when that's 2. That's 2 when that's 3. So it's n minus 1 when that's n. Yes? And of course, look what that becomes. Right? Yes? Maybe? Okay, maybe. So watch this. You can do arithmetic sequences are always the number they start at plus how much it changes by times n minus 1. And you can see why, because that has to be 0 for the first two. So it's always going to be n minus 1. Maybe? Now you guys didn't think about that. You guys that 3n minus 1, you just noticed that it just sort of fit? Okay, maybe. Are you guys okay with that? You guys okay? So what's funny is every arithmetic sequence that exists works that way. Right? Okay, maybe. So, for example, what if I had this sequence, what do you got, Jeff? Let's do 53, 49, 45, 41. So the first element is 53. Changes down 4 each step, right? And of course, this is always going to be
N minus
n
1.
minus 1. So this will be 53 minus 4n plus 4. That's n minus 4n. So it works if it's increasing or if it's decreasing, and you know, hidden behind the scenes is just we're creating the equation of the line that goes through those points. That's really all we're doing. Maybe? Okay. All right. The enthusiasm level went down a little bit. That's fine. So this sequence is based on addition and subtraction. What do you think the next one's going to be based on?
Multiplication.
Oh, shit, yeah. Oh, yeah, it is. Okay. No joke. It's based on multiplication, but you can think of division doesn't really exist, right? It's multiplication by the reciprocal. Right? Subtraction doesn't really exist. There is no spoon, that kind of thing. There is no spoon. It's a part of the matrix. This is the arithmetic sequence is not gonna be as big of a part of this class. It is gonna be a big part of 11.1, or it's gonna be in there. Geometric sequences are gonna be huge. Huge. Unfortunately, it starts with the letter G, but oh well. It's not A for add, so it must be G for go forth and multiply. So, for example, if I have 3, yeah, let's do more. No, let's not do that yet. 6, 12, 24, 48, blah, blah, blah. So it's going to build this one up a little bit. So A1 is 3. To get to A2, what do I do to 3? And to get to A3, I take what I just did and multiply by another 2, yes? So I can put a 1 there, and what can I put here? How many 2's do I multiply here? None of them, yeah. Just want to stay at 3, right? So that kind of feels the same as arithmetic did. I don't want to take any steps. Now I want to take 1 step. Now I want to take 2 steps to get to the next. Yes?
Could that also be 3 times 2n minus 1? Or
Oh, yeah, that's good. What it's going to be. Yeah. So then I want to know an. Good job. It's 3 times 2, like Ricardo said. This is going to always be 1 less than n. Now, dear God. Okay, this is huge. And by the way, my God, real quick. Anybody who thought this was equal to this, just no. Roar. Yes? If you're not sure why that's not true, just come see me. I won't roar at you. I'll explain it. So this is not good to believe that. Now, on the same level, can I do anything with this? I like it. It's probably a good idea to just not say anything. I know, but does anyone think you can simplify that?
No.
What would you say to the person that does this?
You're special.
say goofy
What's up? You say erase that before Wallace sees that. Right? Everybody sees where that came from, correct?
Mm-hmm.
Do you know why that's not true?
Yes.
Because they're not.
It's not the same.
How many 3's are in here? 1. How many 2's are in there?
N
minus one of
one.
them. I can't make 6 n minus 1s if I only have 1 3 and n minus 1 2's. I can't do it. If you look at it on that level, it immediately makes sense. What do I need to make n minus 1 6's? I need n minus 1 2's and n minus 1 3's. I ain't got that. I can't do it. Is that cool?
Mm-hmm.
Holy shit, because this is going to suck if you do that, because then all of it's going to be wrong. Okay, maybe. It's also order operations, correct? What do you have to do first? Exponents. Yeah, so you can't multiply until you do that, and we can't do that, so, oh well. Okay, maybe. Okay. So this is called geometric sequence. And by the way, I didn't do this, I'll do this right now. For a geometric sequence, it's basically A1 times R to the n minus 1, where R is what you're multiplying by. R stands for ratio. So like, what's the ratio of 6 to 3? 2. 12 to 6. 2. And that's how we knew this was 2, yes? So R is the common ratio. It's what the ratio always is. You guys with me? So that's the form. In this case, it was 3 times 2 to the n minus 1. So that's geometric. For arithmetic, it's A1 plus D times n minus 1, where D is the common difference. We look to see how much did it change each step I took. The difference between the two, yes? Okay, maybe. maybe. Okay. Those are two very basic standard sequences. Yes?
And then once you have that figured out, you can basically just plug in whatever, and then.
Yeah. If you give me an A1, you give me an R, I can just create the, right? I like it. Oh, let's see. Okay. So there's some standard sequence things, some standard sequence generators, some standard types of sequences. Fibonacci is just a special sequence. Arithmetic, geometric, they show up all over the damn place, right? Okay, I like it. So a lot of this first homework is just going to be either they give you a sequence and you have to determine what AN is, or they give you AN and you have to calculate the first whatever sequence elements. And that second one is like desperately easy, right? Just plug stuff in. Yes, maybe? And you're like, I don't trust you, Jeff. Let's see. Let's see what happens. What have I done? There you go. Nice job.
He says something easy.
Okay. So, of course, I can have a sequence like this, for example. Right? Anyone tell me anything about that sequence?
That
Getting smaller.
All right, I love it. It's decreasing. Right? The first element is 1. And then it's 1/2, 1/3, 1/4, 1/5. Constantly getting smaller, correct? Does it have a limit?
Yeah, the seed can't be 0. Oh, yeah, put a 0.
0, right? Now, is 0 an element in the sequence? No, because of course that's it's not what limit means. I can't get to infinity. But if you had to tell me one thing about the sequence, they're all getting smaller, well, be more specific, they're all approaching 0. You can get arbitrarily close to 0 if you go far enough out on there. I can bring it down to epsilon and delta. Let's see what kind of reaction. Who did epsilon delta in the Calc 1 course? Anybody? You did?
We barely
You did?
touched it.
We talked about it a little bit, but I didn't have time to get into it all the way.
Yeah, we
which
didn't.
sucks.
We never tested on it either.
No, it's way too nice to hear. So this is 0. So let me ask you this: based on this, the way this word has shown up before now, would you say that this sequence is convergent?
Yes.
Totally, right? What does it converge to?
0.
0. I love it, right? Does it get there? No, but that's not a condition. You with me? So we know ever since we created limits, we wanted them to do a specific job. I can't get to this place, but I kind of want to know what would happen if I got close to that place, right? So normally we see stuff like limit as n goes to 1, 1 over n minus 1. I have to be more specific. I can't get to 1, but I want to know what's happening when I get close to 1, right? So that is exactly useful for sequences. I can't get to infinity, but I want to know what's happening in the long run. So tell me this. Does this sequence, so it's convergent? By the way, does it have to be 0 to be convergent?
No.
No. It just has to be a number. It can't be some kind of infinity, right? Okay. Let me say a few more things about this before I put another sequence up here. Is this always decreasing?
In this equation specifically? Yeah.
Yes, right? It never goes back up, of course, right? Every single term is smaller than the one before. So I could say like this. Does that make sense? an plus 1 is less than an. Blanket statement, right? The next sequence element is smaller than the one that came before it. Is that true for every sequence? Hell no. It's just true for this one. And maybe some other ones. I don't know. So whenever you have a sequence that is always going up or always going down, it's called monotonic. All right? Doesn't mean you just use one type of tonic to make your drink. No, it's monotone. Right? Have you ever heard the word monotone? Somebody speaks in a monotone, so they're talk like this, and he's talking about. I had a teacher who talked like this. It's where he always was.
That was my last
and we
calculus
all went
teacher.
insane. Yeah. Okay.
It's really bad.
So I try desperately not to do that to you guys, because that would suck.
It does.
Everybody understand the idea of monotonic? It just can't come back up on itself, right? In fact, do you guys remember one-to-one functions? What were one-to-one functions? What did it mean if a function was one-to-one? You guys remember?
Every x input is one y output. Yeah.
True. It also meant that it was invertible, and it had to pass the horizontal line test. Is this right? So those were a type of monotonic sequence. In order for a function to be invertible, it had to be monotonic. It couldn't come back, it couldn't suddenly start to go the other way. Does that have anything to do with what we're doing? No, but it's a beautiful example of something you've done before, and we just didn't use this word when we could have. Okay, I like it. Let me see. Yeah, that's good. So what about this function?
That's not monotonic.
Yeah, it's not monotonic. I love it.
It does the loop. The one.
Is it convergent?
No.
Pretty much again, you can do the same symbol, the same thing you just did, right? What's it actually doing? It's constantly going up and down. Now it's a little weird because radians is the standard thing. But if you did cosine 1, cosine 2, cosine 3, cosine 4, you get all these different outputs. They would all live between -1 and 1. So this is not convergent. Does it go to infinity though? All right, so there's a different way to be not convergent than just going to infinity. You just don't get closer to some number. That's all. So it's constantly just bouncing back and forth. Is it getting closer to any single number? No. So that's known as an oscillatory divergence. Ooh, now that's a cool freaking phrase. What do you guys talk about then? Oscillatory divergence. What about you? I'm sorry, I missed a hint. Yes?
Is that like at all related to range and stuff like that? Or?
Yeah. We're talking about the range of the function, right? The outputs would be the sequence elements, right? So for any given input, the output would be a sequence element. And I want to know what are those sequence elements doing. So I want to know what are those outputs doing. So the range of the function is how far up and down the outputs can go, how far up and down the sequence elements can go. Good. It's not convergent, it's oscillatory divergence. I like it. This should be an automatic. Would you say it's bounded? I think I might have already said that. Yes. Is it bounded only above or only below?
Both. Between 1
Bounded
and
both.
0.
So if it's bounded both above and below, you just say bounded. What about this one?
Bounded below.
Below, yeah. Officially it's bounded below. I know it starts at 1, but it's bounded below. It doesn't like oscillate between 2, right? It just continuously goes down, but it's bounded below. Is that cool? So the idea of bounded, you might have used that exact word before, but it means exactly what you would hope. And trig functions are the obvious ones to talk about bounded. But you can be bounded below, bounded above, right? Those horizontal asymptotes you guys did in pre-calc? Yes? Okay.
Well, isn't that one kind of bounded above 0 though?
Say again?
Because it can't dip below 0, wouldn't it be bounded on both sides?
That's what I'm saying. This is bounded below by 0.
Okay.
It's not really technically bounded above because the minute it starts to go down, it doesn't really have a ceiling technically, although it can't go above 1. We're talking about what is it doing once it gets started.
Okay.
Right? What's this doing once it gets started? Bounded above, bounded below. Right? Yeah. I like it. How are you guys doing with the terminology? It's not that bad. Some of the terms you should have heard before. We've definitely heard convergent, divergent before, right? Even before the semester, hopefully. Okay, so let me throw a theorem at you. I don't know what number this is in the book. Okay, screw it. This comes later. I'm doing this all out of order. It doesn't matter. If AN is bounded and monotonic, then it's convergent. Monotonic, so it starts going in some direction. It's bounded. So it's always, so for example, if it's always increasing, because monotonic could either be going down or up, if it's increasing and it's bounded, it must converge, correct?
Mm-hmm.
I like it. How's it different from him? He's bounded, but he was oscillatory. Oh shit, so he can get away and come back and get away. This guy can't escape. It's like, I don't want to converge to you. Ah, shit. Right? Okay, I like it. Okay, so let's back up a little bit.
When you say bounded, does that mean on both sides or just?
Yeah, if I say bounded, that means above and below.
Okay.
It's sort of like, if I say find the limit as x goes to 3, that means from both sides. If I want to be more specific, plus or minus, so here I'd have to say bounded above, bounded below, if I want to be specific.
Okay.
Yes?
Does the sequence formula also have to be continuous for all natural numbers?
I like it.
But if you had something like 1 over n minus 3 or something like
I mean, to be able to do anything worthwhile with it, yes. Right? And there are certain theorems and such we're going to use that it requires the sequence to come from a function that is continuous, right? But a sequence doesn't have to be.
I mean, to be convergent.
Oh, to be convergent. Now that's interesting. So, yeah, if I did this, and I said it was this, so AN is this, right? What's A1? Infinity, right? Right? And then A2 would be 1, and A3 would be, and so forth. So this sequence, it depends on what you're doing with it. You can still say this is convergent in the long run, because again, what does this limit care about?
Infinity.
Does it care about n equal to 1?
No.
It just cares about really big n. It doesn't matter what's happening before n gets big, right? So it depends on what you're trying to do with it as to what conditions the sequence has to meet. Does that make sense? But just in general, it's okay if it's undefined at some parts. This question just cares about in the long run, right? So this is convergent as n gets big. What would be interesting is the next thing we're going to do is we're going to add all the sequence elements together. In that case, this would have no chance for that addition to be convergent. Does that make sense? So if I take a sequence and I just start adding all the elements together, we're going to ask, is that convergent or is it divergent? That's the next thing we're going to do. Okay. Yes. So a couple of little things about sequence limits. They have to limit, just to make this official, we basically said this earlier, then AN is convergent. So that just captures that idea, right? Where L is a finite number, correct? So L could be anything except infinity or negative infinity. Okay. Otherwise, it's divergent. And remember, in order for a limit to exist, it can't be like that function over there. That limit does not exist, even though it doesn't go to infinity. Right? So don't think this is a strong dichotomy between it's infinite or it converges. That's not true. There's a good example of not infinite, but not convergent either. Is that cool? So convergent means it's got to start to get arbitrarily close to some number. This never does that. It's always just bouncing bouncing, 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 and never gets close to some number. Maybe. So that's something we've already said. I just wasn't that technical about it. Oh, this is kind of interesting. This is really going to become huge. If the limit as, how do I want to put this? Yes, I like it. As x goes to infinity, of f of x equals L, then the limit as n goes to infinity, f of n is L. So I just want you to think about what that's saying for a minute. Maybe it seems like I said the same thing twice. Does anyone see how I did not say the same thing twice?
One's a function. The other is sequence.
Here, what are the inputs? What kind of numbers? Here, what are the inputs? Anything. So, isn't this 1 over x, right? Isn't that the positive? You with me? So this is f of x equals the positive part of 1 over x. Cool? Where is 1 over n?
Everywhere?
1. It's those points. You guys with me?
Mm-hmm.
You with me? Okay, I like it. This is going to become really big, believe it or not. Why? Can you do the derivative of this?
Yeah.
Yes, the right answer is in my sleep, Mr. Waller, right? That's the right answer. In my sleep. There you go. Okay. Can you do the derivative of points?
No.
Does that even make sense to say?
No.
No, because you have to have, it has to be connected, it has to be continuous. I can't do the derivative at a point that's only made up of points. So there will come a time relatively soon when we're gonna wanna do, in fact, let's just do it right now. It's really simple, right? Let's see if you guys, see if I can find a really quick example. Blah, blah, blah. There you are, I love it, okay. So let's say I want to know if this converges. Oh man, there's a lot of n's.
Is that natural log of it?
Say again?
Natural.
That's natural augment. Let me make it. So how do you figure out if that's convergent? What do you check? The limit. And what really cool thing did y'all learn last semester that some of you guys tried to use too early? Yo, damn it.
L hospitals.
Oh yeah, good. El Hospital. I like it. Somewhere he's rolling over in his grave. Or maybe he's like, it just made some dead guy laugh. It's pretty good with her. So, l'hôpital, right? When I say that, does that bring back any memories? Can I use it on this? Yes. Hell no. What did we just say? Can I take a derivative of a function made of separate points? No. But didn't we just have something earlier that talked about if the limit as f of x, if that converges, then so does the limit n. Yes?
So ln of x
So
over x.
you replace this,
Oh,
investigate,
starting over.
investigate? Sure, Jeff.
Investigate.
Oh my God, we gotta investigate. Investigate the limit as x goes to infinity. Because whatever this guy does, this does. Because these, I really want this to make sense. Whatever this looks like, these are specific points sitting on that function. So whatever that function does in the long run, so does so does the points. But you officially have to make it like this. You cannot do L'Hopital's to this. You cannot, because derivatives are not defined for separate points. So how does L'Hopital's work?
Take the derivative of the top and the bottom separately.
Yeah, you just do the derivative of the top and the derivative of the bottom, the ratio of those. You don't do quotient rule. That's shit. You don't need that for L'Hopital's. You just do derivative. What's the derivative of the top?
1 over x.
What's the derivative of x?
1.
Dang it straight. You need to make that an x, Jeff. Good job. And of course, what's that?
0.
Sorry.
Is that just a notation thing? Because if the function was like a function of n, then it could be ln over n instead of f of x.
Again though, what does this mean the inputs are?
No.
1, 2, 3, natural numbers. Is that a continuous function? No. And what do you need in order to be able to do almost most calculus things to a function? It needs to be continuous, right? So this feels like not a big deal, but this is huge. We're actually saying, looking at the continuous realm of all the things that lie on this, whatever this does, then these specific things that happen to lie on that curve will do the same thing. So this goes to 0, so is this convergent? Yes, because and it will also go to 0. I like it. Now real quick, why does it make sense? What grows faster? What does natural log look like? Can you guys trace it in the air for me? What's natural log look like? Yeah, doesn't it really slope down and just get flat almost immediately?
Yeah.
So what grows quicker, n or natural log of n? N grows quicker. So this is like really slow divided by really quickly growing. So of course it's going to go to 0, right? But just L'Hopital's. Why does L'Hopital's make sense then? Because I'm looking at the rate of change, which is exactly what we just said. It's all about who gets there quicker, right? They both go to infinity, correct? It's just the top gets there slower than the bottom. So of course the whole thing goes to 0. Are you guys? Like 110, 200, 3,000. Aren't they both going to infinity, the top and the bottom?
Mm-hmm.
But the whole thing is going to go to 0, of course, because the bottom is just growing so much faster. That's why L'Hopital's make sense, period. Right? It analyzes who's getting to where they're going quicker. Maybe. Okay. Oh yeah, here's some boring shit. Page. Wait a sorry. This should be really obvious. You remember learning about limits, and there were the limit laws, like the limit of f of x plus g of x equals the limit of f plus the limit of g. Remember those? And they were just like, yeah, I get it book, right? So if you have your book with you, you don't just write this down in your notes, page 697 at the bottom, there's a bunch of limit laws which should make crazy amounts of sense, right? So let me ask you a few questions based on these. Even if you don't have it, you should know this. If the limit as n goes to infinity of f of n, if that is 3, what is the limit as n goes to infinity of 2 times f of n?
2. No, 6.
6. Isn't that incredible? That's one of the laws in the list of laws. Do I need a law to tell me this? Of course not. We know that constants can come outside of limits. We know that already. So basically, those limit laws are the same limit laws as before. Okay. Page 697. You might want to take a look and verify for yourself. They're exactly the same limit laws we learned when we first learned limits. It's just they're now talking about 2 sequences. So for example, what do you think this is? See, I have 2 sequences now. I have the sequence AN and the sequence BN. AN could be 1 over n, BN could be n squared minus 3n. I don't care. What do you think the limit of their sum is?
Infinity?
I don't know what they are. They could both go to 0. So this is almost too basic, maybe. It's equal to the limit of AN plus the limit of BN. Yes? We've seen that kind of limit law before. Before it was f of x and g of x. Now it's AN and BN, 2 separate sequences. Are you guys with me at all?
Mm-hmm.
So I'm not going to make a big deal out of that. They're not amazing. They're the same limit laws we knew from before. Okay. So limits have come back. They haven't brought, there's nothing new about them. Nothing new about them. Just what they're operating on is new, these sequences. Okay, that's really all this is saying is, hey, guess what? They work the same way as before. Okay. Oh, here's something interesting. What if the limit as n goes to infinity of the absolute value of an was 0. Can you say anything about an? Say again? Why?
It's multiplied by 0?
Say again?
It's multiplied by 0?
No, nothing's multiplied by 0. Right? Is everybody cool with this limit of the absolute value of n?
A of n equals 1 over n? To some degree? No?
No, no. No, there's a ton of sequences whose limit is 0.
Okay.
They just are. 1 over n is one of the most basic ones. What about 1 over n squared? Yeah, okay.
1 over n cubed.
Yeah, it's amazing. There's a whole family called 1 over n to the p. It's crazy. So yeah, what you said earlier was right. Yeah? If the limit of the absolute value is 0, meaning, for example, if I took the absolute value of sine, wouldn't it look like this? Right? Is that limit 0 though?
No.
No, it's kind of like oscillating now between 0 and 1 because it's not allowed to go negative.
It's
Correct?
monotonic?
Say again?
It's monotonic? Is that?
No.
This is definitely not monotonic.
No, I mean in this case. If
I don't know. Doesn't have to be. No.
If the absolute value is equal to 0.
So I want to know if
A
this
to the
is
n
true.
is equal
What
to
can I
0.
say about
Right.
this?
That's it.
wait,
That's also equal to 0.
wait a minute.
Exactly, because let's look at it this way. Instead of geometrical, instead of visual, what does that mean about the sequence elements? No matter what they are, negative, positive, they're all getting really small. So if I just take the absolute value away, some are going to be negative, possibly, yes? Aren't they still getting small? In this case, when we say small, we mean closer and closer to 0. Yeah, so of course that's 0. I like it. And so many women are like, that's what I freaking said. But I wanted everybody to come with us. Okay. That's going to become huge eventually.
Feels too easy.
Right now, that seems like, okay, it's a little throwaway, a little side note. That's going to become huge. Okay. So there's a lot of groundwork being laid here. There's just basic definitions, basic terminology, but there's also a few things like this, which is going to become huge later this section, later this chapter. Okay. Now, let me ask you about this here. Given r greater than 0, right? Is there anything we can say about this? Now, this is one of the coolest freaking things. This is another one that's going to come back over and over. So let's analyze this. Let's look at this sequence. Somebody give me an R. That is true.
2.
2. What sequence does this create? So what's A1? 2, right? 2 to the first. Are you guys with me?
Yeah.
R is 2. Somebody pick 2 for me. So it's 2. What's A2? 4. So what's 2, 4? And? Okay, does that converge?
No.
No. In fact, wouldn't you agree with me that 2, 3, 4, none of those would converge? Now, did I say R had to be a natural number? R is just greater than 0, right? What about if R was 1.5?
It would still.
Let's try it. What if R is 1.5? And let me stop for a minute. Does everybody understand what's happening right now? So I want to look at R to the n, that sequence, where R is just some positive number, correct? So we're going to analyze this, and I'm trying to figure out, let me just say this exactly directly. Is there a place where it starts to converge? Because we already saw, if R is 2, we get this sequence, yes?
Yeah, when it's less than 1.
Or it could be 1, 2, right?
If R is 1, what's the sequence? What's 1 to the first power?
1.
1 squared.
1. 1.
That is convergent to 1, right? Now let me put it even more directly. When is the limit? So it's convergent at 1, definitely not above 1. When is the limit 0 though?
When R is less than.
Yes. Numbers that are less than 1 are the only numbers that get smaller when you multiply them together. What's 0.9 times 0.9?
0.81.
0.81. Times 0.9 again. 0.729.
Okay.
Thank you for playing. And then it just keeps smaller and smaller, yes? Does that make sense? And that's why they actually, that's why a parabola curves down, yes? Have you guys ever noticed this? So parabola curves down and then up. So here's the y equals x line. It's below 1 and then it shoots above 1. And I've never analyzed a parabola that closely, but you guys understand what's happening? So for numbers that are between 0 and 1, when I multiply them by themselves, what's 0.6 times 0.6? 0.36. It gets smaller, doesn't it? But the minute it gets to 1, now it matches. 1 times 1 is 1. Now once I'm past 1, I shoot way up from y equals x. Not a huge discovery, but I don't know if any of you ever thought about it like that. That's why the parabola curves down. In fact, do you guys know what x to the 10th would look like? It would look basically like this. I mean, it's just 0.9 to the 10th power. Can somebody do that real quick? What's 0.9 to the 10th power? 4, 3, 2, 1.
0.38.
Oh, I was almost there.
0.34867.
0.34867?
0.9 to the 10th?
0.9 to the 10th?
Yeah.
Okay,
0.34.
wasn't expecting that. Okay. 1, 2, 3, 4, 5. I'll let it go in a minute. 6, 7, 8. Maybe it's true. All right. So it's really tiny. It's really tiny is the point. So it starts to look more like just like this. If you graph like x to the 100th power, it's gonna look like bam, bam. It's gonna look like that. It's crazy. Okay, enough. Sorry. So if r is less than 1, then the limit of this is 0. That is going to become crazy huge. And why do we use the letter R? Because this is a lot like a geometric sequence, right? It's exactly like a geometric sequence. Are you with me? Okay. In fact, real quick, here's the last thing we'll do, and then I'll let it down way early. Because I'm tired and you're tired, and
I'm hungry.
the room, I can just feel the room has just had enough of this. But this isn't too bad, right? This isn't too hard.
That's just there.
Yeah, just theorems, which are always exciting. It's not too hard yet. I have a handout I'll give you before you leave, so don't go anywhere. What was I about to do? Oh, yeah. What was the geometric formula? It was this guy here, right? It was A1 times r to the n minus 1. What if A1 is r? So for example, 2, 4, 8, 16. Isn't A1 2? And isn't R 2? 2, 4, 8, 16? You guys with me? What if A1 is R? Then what is this? R times R to the n minus 1. What is R times R to the n minus 1?
R squared. R
Add powers?
So r to the n.
Yeah, R to the n. Right? So that is a special geometric sequence where the first element happens to be what you keep multiplying. So 3, 9, 27. The first number was 3, and I keep multiplying by 3. Yes? Maybe? So this is going to show up in a big way, not too far from now. So let me give you this. I want to say a few words about this, so don't go anywhere yet. Don't get too excited.
Well, I moved it that way because he was doing stuff all the way over there.
So on one side of this is
More like a help
sequences. On the other side, if you want to freak yourself out, we will be talking about the other side. It's one of my favorite things ever. Something called math induction.
Induction.
I don't know, has anybody ever heard of math induction?
No, but I'm excited.
Yeah, sweet.
Is there a different name for that somewhere?
I don't know. People can have all kinds of names for things. Trust me, I've heard many. Real quick, I want to point something out. I kind of am curious if anybody can figure out why, like the first two sequence, like there's Fibonacci as part C there, right? You guys see that Fibonacci?
Yep.
But then you got triangular and pentagonal numbers. So anybody might be curious why the hell we call those triangular and why we call those pentagonal, right? So up here, right? You guys with it? A and B up there at the top. So maybe we'll talk a little bit about. Then I had a few exercises here. You guys should all be able to do those. We'll talk about those next time. Which one of those is recursive? Those 4 problems.
Fibonacci.
Which one of these is recursive? These 4 exercises right here.
4.
Yeah, number 4.
Yeah.
And then I talk about limits, and I bring up L'Hopital's. I give you an example in case you forgot how to do that. I also thought there's method number 1. Remember the finding horizontal asymptotes, where you look at the highest degree term? Remember that? So I give you a little reminder about how that works. All right, so we'll do some of these next time just to review what we did today. Cool, I think that's everything. If you didn't get your test back, just come up and see me. Otherwise, I will see you guys later. I'll give us all an early night.
Appreciate it.
Yeah, God bless.
Thank you.
Sure.
God
Get used to it.
bless.
I already did my corrections.
Sweet.
This is the bonus that I didn't try to correct the bonus.
All right, I should have said, you only get